And I'm going to share my screen. All right, so I am in Blackboard. I've gone to course content. So from the left navigation, go to course content. And I'm going to scroll down to the particular chapter that we are in, chapter 2. And if I click on a specific section of that chapter, for example, section 2.5, 2.5, I can see all the videos that Pearson has created for this section. So there are lots of videos available. Now, because I was creating them rather quickly a couple of semesters ago, does anyone remember when COVID started? When COVID started, I quickly created videos for the chapters. And if I go into course content and I go to the chapter and I scroll to the bottom, there are Professor Castle's lectures. Now, I don't have a lecture for section 2.8. That was because in 2020, we weren't actually covering section 2.8. Now we are. So I do need to create a video for section 2.8. But these are all my videos that I have uploaded to YouTube. So you need to watch the section 2.5 transformation of functions video on your own. Now I will pull this video link out and put it in an announcement later today when I upload the recording of today's meeting, which I will do here in just a little bit. All right, so we are going to concentrate then today on sections 2.4.3 and 2.4. And then you are going to do section 2.5 on your own in the next week. All right, so when we left off last Thursday, I didn't have time to do the difference quotient. And I said that the difference quotient is extremely important. And my assumption is all of you are moving on in mathematics. That's why you're taking college algebra. College algebra is a precursor to trig and calculus and any other mathematics you want to take. So the difference quotient is extremely important in calculus. As a matter of fact, it's one of the first things you learn in calculus because it's the way you learn to take a derivative. So we are going to look at the difference quotient. And the difference quotient just beautifully segues us into the topic of slope for linear functions. So linear functions are functions when you draw them, they're straight lines. Linear functions have slope. They have slantiness, if you will. So this difference quotient is basically a slope. All right, let me get my PowerPoint started here. All right, so here's the difference quotient. Can everyone still hear me okay? When I flip my laptop around, I hear beeping and I'm wondering if I disconnected. All right, so what this is, this difference quotient, let's just draw a random function. Just draw something. So here's my function I just drew. And if I look at the change in the value of the function, the y value, so remember y and f of x are the same thing. So if I look at the change in the y direction, so this change from these 2 points, let's call this x, and let's call this x plus h. So that distance in that little right triangle I've drawn, this distance right here, let's highlight it. This distance right here is h. So the first point is at some arbitrary x. The second point is a little bit farther than x. So h is infinitely small. Now it says h can't equal 0, but we're actually going to let h approach 0. So h is infinitely small, very small. So if I find the change in the y over the change in the x, that's the difference quotient. Because if this function, this point on the right, if its x coordinate is x plus h, then its y coordinate is the function evaluated at x plus h. And if this point down here is x, then its y coordinate is f of x. So we're finding the change in y over the change in x. So we're actually finding a slope, which we're going to talk about in just a minute, a slope of the line that connects those 2 points. That's what the difference quotient is. So how do we find the difference quotient? Well, it's a matter of taking a difference in 2 function values and then being really careful when we do that, because we're subtracting f of x, which f of x is a function, and so it can have, it can have 20 terms in it. So it's a function that we have to carefully subtract. All right, for example, our function is f of x equals negative x squared plus x plus 5. And as you get to section 2.5, that's a quadratic function. It's quadratic because of the x squared there. So let's find the difference quotient using a quadratic function. So the first thing I need to do is evaluate this function at x plus h. So what I do in my function, wherever there's an x, I replace it with x plus h. So I'm going to have negative 2 times x plus h squared. So where there was an x, I replaced it with x plus h plus x plus h plus 5. Right now I'm going to simplify this. First of all, I saw this on a test. I saw someone do this. And I'm going to tell you, no, you cannot square a binomial and get the sum of 2 squares. Are you all listening to me? You can't do that. No. When you square a binomial, what happens? You square the first term, so you square the x. Then you multiply the 2 terms together and you multiply that by 2. And the reason that works that way is because outside and inside are both xh. xh plus xh is 2xh. So you multiply the 2 terms together and then multiply that result by 2. Again, I'll be nicer this time. Never in a million years. Never, ever, ever, ever. Did she say that enough? And then you square the last term. Never. Okay, now we're going to distribute the negative 2 across. So I have negative 2 times x squared. Negative 2 times 2xh is negative 4xh. Negative 2 times h squared is negative 2h squared plus xh plus 5. And there's no terms that I can combine when I do this. So the first step of this is just to evaluate the function at x plus h. Now the next step is actually to subtract the original function from this big O long expression. So we're going to, sorry about that. We're going to take this f of x plus h, and we're going to subtract the original function. And the only thing tedious, this is just tedious because you have to keep writing stuff all over and over again. Okay, and now I'm going to subtract the minus 2x squared plus x plus 5. And as you recall, if you're subtracting an algebraic expression, you change the sign of everything on the inside of those parentheses. So we're going to get negative 2x squared minus 4xh minus 2h squared plus x plus h plus 5. I'm going to distribute that minus across. Minus a minus gives me plus 2x squared minus x minus 5. Now, if you had done this correctly, every term that's a constant or only contains an x should add to 0. You should be left with only terms that contain an h. So look at this. We have negative 2x squared. We have positive 2x squared. Negative 2x squared plus 2x squared is 0. I have plus x. I have minus x. X minus x is 0. I have 5 minus 5. 5 minus 5 is 0. So what am I left with here? I am left with negative 4 xh minus 2h squared plus h. And then I'm going to take that and I'm going to divide the whole thing by h. And here is another thing that I saw on your exams that I'm going to yell at you about. I saw you guys using the quadratic formula. Lovely. You were doing a good job getting things plugged in, but then you started canceling willy-nilly. And guess what? You can't cancel willy-nilly. You can only cancel something in the denominator of a fraction if it's in every term of the numerator, because you must be able to factor it out of the numerator. And if you can't cancel it. If you can't factor it from the numerator, you can't cancel it with anything in the denominator. That is a law. You can't do that. So I factored out the h from the numerator, and then I'm canceled that with the h in the denominator. So what I end up with for my difference quotient is negative 2x minus 2h plus 1. All right, so what's the significance of this? Well, it has major significance, because this leads us to what's called the instantaneous rate of change when we're talking calculus. So if I take my difference quotient and I take the limit of that as h approaches 0. Now, remember, they told me h can't be 0, but h can approach 0. I mean, h obviously can't be 0, because if we have 0 in the denominator, the universe explodes. So you can't do that. So we're going to let h approach 0, but never quite reach there. So what was our difference quotient? Our difference quotient as h approached 0 was negative 4x minus 2h plus 1. So if we let h go to 0, that entire term goes to 0, and we get negative 4x plus, I got something wrong here. No, I don't. I'm good. Having a moment. I get negative 4x plus 1. And negative 4x plus 1 is the first derivative of that function. And what does the first derivative measure? The first derivative measures the rate of change. That is what it measures. And it's called the instantaneous rate of change. So at any value of x on this function, I can calculate its rate of change at that point. The instantaneous rate of change at that point by just plugging in a value for x. So this is very important. And it leads us to our discussion of slope and then average rate of change in section 2.4. So all this stuff is the instantaneous rate of change. It's the first derivative of a function, which you don't have to worry about until you get to calculus. But we're going to talk about the average rate of change, which is also important, here in just a minute. All right, so that's the end of section 2.2, which I promised you last Thursday I would go through. So next, we're going to talk about slope. So we are going to focus in section 2.3 only on functions that are linear. So we're going to forget functions with any other shape for a minute, and we're only going to look at functions when we graph them, we get lines. All right, so this is an example of you, a researcher, taking data. So you get a bunch of data that compares the percentage of adult females who are literate versus the infant mortality rate. And I'm not sure the context of this information. I'm not sure if this is their children or exactly what it is, but that would be my assumption from the graph. And we can see as X, which is the percentage of adult literacy, increases, it goes to the right, the infant mortality rate decreases. So there's a relationship, which we can see, between these two variables. As a matter of fact, the relationship, viewing the scatter plot when we plotted the data, appears to be linear. So as the adult literacy rate increases, the infant mortality rate decreases. So it's linear and it has a slope. So the slantiness, how much this line drops compared to how much X increases, is called its slope. So the slope of a linear function can be found by taking the change in Y over the change in X, which is exactly what we did just a minute ago and when we looked at the difference quotient. So if we have 2 points on a linear function, and we're going to designate these points using subscripts, and subscripts simply mean they're different. So I have 1 point X sub 2 and Y sub 2. And then I have another point X sub 1, Y sub 1. And that just designates that those are 2 different points on the graph of this linear function. To find the slope, I find the change in Y over the change in X, or the rise over the run. So I take the Y coordinates and I subtract them, Y sub 2 minus Y sub 1. And I take the X coordinates and I subtract them, X sub 2 minus X sub 1. And that ratio of the change in Y over the change in X is the slope. And we use the letter M to designate slope. Anytime you see an M in mathematics, if it's in the context of functions and linear functions specifically, it means slope. So how do you find the slope of a line given 2 points on the line? It's literally a plug and chug. And so what I do is I make myself a note which point I'm going to let be the first one and which point I'm going to let be the second one. And this just keeps my signs straight. So I'm going to let X sub 1, Y sub 1 be the first point, and X sub 2, Y sub 2 be the second point. Literally first and second in the order that they came in the problem description. All right, and then I'm going to plug those in. So I have 5, Y sub 2, well, let's write that down. X sub 1 is 4, Y sub 1 is -2, X sub 2 is -1, Y sub 2 is 5. So we're going to plug that in. So in the numerator, I get 5 plus 2. In the denominator, I get -5. So my slope is 7 over -5, which is perfectly fine to write it that way. If you have a fraction that sign is negative, that negative may be in the denominator, or it could be in the numerator. They mean the same thing, or it could be outside the fraction. So 7 over -5 is the same fraction as -7 over 5, which is the same as -7/5. So they all mean the same thing. Well, what's this mean? Well, depending on which one of these versions you use, well, you're going to use one of these 2 versions. It tells us what happens from one point to the next. So we're going to go over on our coordinate plane and we're going to quick graph these 2 points and we're going to look at what happens with the slope. Okay. So I'm going to graph 4, -2. That was my first point. 4, -2 is right there. And my second point was -1, 5. And I'm going to draw some dotted lines here. And we're going to go from one point to the other because these are 2 points on a line. Okay, so if I take, now that I've got it drawn, if I take -1, 5 to be my first point, to get from -1, 5 to 4, 2, I got to go down 7. So that is my rise. So I'm going down 7. So my slope is going to be -7 over. And then I have to go right 5. So my run is going to be 5. So my slope is -7 over 5. Or I could go the other direction. I could go up 7 and I could go left 5. So to get from 4, -2 to -1, 5, I'm going to go up 7 and to the left 5. So my slope would be 7 over -5. Gets me to the same place. Gets me from one point to the other. So it doesn't matter which way I go. But I don't know what I was going to say. Now, if we drew this line between these 2 points, we could see that it slants down. Let's draw a line through those 2 points. It slants down. That's because its slope is negative. So lines who slant downward are going to have a negative slope. So here are our 4 cases of lines. The first 3, these 3 are all functions, not a function. I mean, it fails the vertical line test spectacularly. All right, so the first graph of a linear function has a slope that's positive. So if it slants upward, as x gets bigger, y gets bigger, then its slope is positive. If it slants downward, as in the second graph, as x gets bigger, y is getting smaller, then its slope is negative. A horizontal line, which is a function, a horizontal line is a function, it's a constant function, then its slope is 0. And then a vertical line, not a function, and its slope is undefined. So since it's not a function, its slope's undefined. It's undefined because everywhere on that line, the x's are the same. And so if you look at your slope formula, you're going to have 0 in the denominator, and you can't do that. All right, so the first form of the line that we have is the point slope form. What's this mean, this form of a line? Well, you can create the equations of lines from their points. So given 2 points on a line, you can find the equation of that line. And you can do that using one of your formulas. And the first formula you have is the point slope formula of the line. If you're given 1 point and you know the slope, you can find the equation of the line. So knowing 1 point and the slope, you can find the equation that describes that line. So given 1 point and the slope, you can find the equation of the line. And I hope everyone is awake, because I had this question yesterday. Someone told me I put it in there correctly. And I said, did you? Did you really? Did you? Okay, so we're going to find the point slope form of the line with slope 6 and goes through the point 2, -5. So our point is 2, -5. and our slope is 6. So we're going to plug that in. I hope everybody's awake. Are you all awake? Give me a thumbs up if you're awake. Give me something. All right. The only thing you need to do is simplify this right here. Done. That is point slope form. Don't need to solve for y. Don't need to remove the parentheses. Don't need to do any of that. I stop right here because this is point slope form. And the reason it's point slope form is I can determine from the way this equation is written, what is the slope? Well, the slope is that number outside those parentheses. The slope is 6. Okay. I can also determine what point is on the line, the graph of this line. Whatever I'm subtracting from x is the x coordinate of a point that's on this line. And whatever I'm subtracting from y, now since it's plus 5, I'm subtracting -5. That is the y coordinate of a point that's on the graph of this line. So the slope is 6, the point is 2, -5, just by looking at the equation. So don't go any farther. If it asks you for in my math lab, for the equation in point slope form, you stop right here. You are done. Now, there are other forms of the line, which we're going to talk about in just a minute. And if they ask you for that form, then you continue on. This is point slope form. All right. So what if you're given two points on the line and they ask you to find the equation in point slope form? Well, again, what do I need to know? Well, I need to know if my pen is red. There we go. I need to know one point. Well, I've got 2, so I'm good there. And I need to know the slope, and I don't know the slope, but I got a formula for it. So I'm going to find the change in y over the change in x. So that's 9 over -6, which I can divide out of 3 because numerator and denominator are both divisible by 3. So I get -3/2. I can only cancel if I can divide the numerator and the denominator by that number. Only way I can cancel. So my slope is -3/2. And then I can pick either point. It really doesn't matter if you use this point in the formula or you use that point in the formula. It does not matter. Both will be correct. I'm going to use the first point because it's first. So I have y minus a -3 equals my slope, which is -3/2. And aren't you grateful that in point slope form, you don't have to multiply this out? X minus 4. Have I got that all in there correctly? X minus a -3 equals -3/2 times x minus 4. No, I don't. Yes, I do. Yes, I do. So I have y plus 3 is equal to -3/2 times x minus 4. And I'm done. That is the answer in point slope form. Right? Because it goes through the point it goes through the point 4, -3, and the slope is -3/2. Okay, so what's the next form of the line? And this seems to be what you all gravitate to, because when you're in high school algebra, this is really emphasized that you need to solve this equation for y. And if you take the equation that I have put in this pretty starry thing, if you take that equation and you solve it for y, that is slope-intercept form. So whenever you take an equation, a linear function, and you have it solved for y, that's slope-intercept form. So slope-intercept form is when your linear function is in terms of y, and we get y equals mx plus b, where this is the slope of my line. So my slope is m. And this number is super duper important. That constant that you're adding to the x term is the y-intercept. Now, we've been looking somewhat at intercepts so far this semester. We're going to look at them pretty in depth here in a minute. But what do we know about a y-intercept? We know that when x is 0, we're on the y-axis. So if we set x equal to 0 in this equation, we get y is equal to b. So b would be the y-intercept. So the number that we're multiplying times x, that is the slope. And then this constant over here is the y-intercept. So for y equals 2x minus 4, the slope is 2, and the y-intercept is -4. And we can use this information to graph. And it's been my experience teaching college algebra for eons that this is the way most of you graph equations of lines. You use the slope and the y-intercept. Now, we can also write in terms of f of x. It is a function. It's a linear function. F of x and y represent the same thing. And the slope here would be 1/2, and the y-intercept would be 2. So how do we use slope and y-intercept to graph the equation of a function, a linear function? So the first thing you do, you're very familiar with this, is you plot the y-intercept. That's your first point on the graph of your line. And then you use the slope to find the second point. If the slope is positive, you go up and to the right. If the slope is negative, you go down and to the right. That's typically the easiest way to go. And then use a line, straight edge. I'm sure you're all going to take a straight edge out. And then you're going to take a straight edge out and you're going to draw your line. So let's use the slope and the y-intercept to graph f of x equals 3/5 x plus 1. All right, so the constant is our y-intercept. So we're going to plot a point at y equals 1. So we're going to plot the y-intercept. And then we're going to look at the slope. The slope is 3/5. So we're going to go up 3. So this is the rise. So we're going to go up 3. And this is the run. And we're going to go to the right 5. So we're going to go up 3, 1, 2, 3. And then we're going to go to the right 5, 1, 2, 3, 4, 5. So we're going to end up right there. And that point is going to be 5 because we've moved to the right 5 from the y-axis. And its y-coordinate's going to be, well, we started at 1 and we went up 3. So we're going to end up at 4. Now I could go down 3 and to the left 5. So I could go down 3, 1, 2, 3, and to the left 5. And that is also a point on the line. Is that -2, -5? So I could do that also, but typically we go up and to the right. So we go up 3 and to the right 5, we end up at 5, 4, and then we draw a line through those 2 points. So using the slope and the y-intercept to graph the equation of a line. All right. You have a couple of special lines. The first one being horizontal, which is a function. So we could write this as a function. Y equals a constant, and you notice we use b because that's the y-intercept, is a horizontal line. It is a function. It's a constant function. We also have x equals a. This is a vertical line. So whenever you have x is equal to a constant, that's a vertical line. This is not a function. The slope of a horizontal line is 0. There's no x term there because m is equal to 0. Over here, not a function, the slope is undefined. Okay, the last form of the line that we get is general form, and this is probably the least helpful, but general form when we're talking about functions is always where we have everything on the left-hand side of equals and 0 on the right-hand side. So if we take a function and we put everything on the left-hand side and get 0 on the right, that is general form. Now, it's not particularly helpful, except if I take the C and move it over here to the right-hand side, I can use this equation to graph using intercepts. It's very, very easy to do. And this is my favorite method for graphing the equation of a line. Okay, so what's the slope and y-intercept of a line whose equation is? Well, the easiest way for me to figure out what the slope and the y-intercept is to put this in slope-intercept form. If I can get it in slope-intercept form, then I can just look at the equation and determine what the slope and the intercept is. So I need to solve this for y. Okay, so the first thing I'm going to do is move the negative 12 over to the right-hand side. When I move that negative from the left to the right, it's going to become positive because I am adding 12 to both sides to accomplish that. And this is the form that I like to use to graph intercepts. I mean, I can just look at that and tell you the x-intercept's 4 and the y-intercept's 2. So this is the form that I like to graph, but we're going to continue on. I'm going to move the 3x over to the right-hand side by subtracting it from both sides. When I move that positive from the left-hand side to the right-hand side, it's going to become negative. Almost done. Now we're going to divide by 6, and I have to divide everything by 6. Every term gets divided by 6. 6 divided by 6 is 1. Negative 3 divided by 6, I can divide out a 3. 3 divided by 3 is 1. 6 divided by 3 is 2. 6 divided by 12, 12 divided by 6 is 2. So the slope is negative 1/2, and the y-intercept is my constant. That's the easiest way of finding the slope and the y-intercept when you're given an equation of a line in general form. Okay, now I like to use general form to graph. If you have an equation of a line in general form, typically, as I said, I move the constant to the right-hand side. It makes things a little easier for me. But to find the x-intercept of the equation of a line, you just set y equal to 0. To find the y-intercept of the equation of a line, you set x equal to 0. You plot those 2 points and you draw your line. So what are the y-intercepts and the x-intercept? What is the y-intercept and the x-intercept of this function, this linear function? I will spit it out. Okay, I am going to move the 6 over to the right-hand side. It just makes life easier for me. So since it's minus on the left-hand side, when I move it to the right, it becomes plus because I am adding it to both sides. And now I'm going to find the intercepts. To find the x-intercept, set y equal to 0. So the x-intercept is 2. To find the y-intercept, we're going to set x equal to 0. And the reason I like this method so much is that I think it's really easy to do. Divide by -2. Because when I'm in this form right here, when I'm circling right now on the screen, see that right there? I can just look at that and pretend that the y is not there. So just get rid of the y term. And I have 3x is equal to 6, x is equal to 2. That's the x-intercept. And then in the same form, I just get rid of the x. So just get rid of the 3x, just get rid of it. You have negative 2y equals 6. So y is equal to negative 3. And that gives me the intercepts really, really quick. So we're going to plot those now. So we have 2. Whoops. Help me out here, PowerPoint. So we had 2 for the x-intercept. And what did we have for the y-intercept? Did we have negative 3? And this works really well. The only time it really doesn't work particularly well is when one of your intercepts is a fraction. And in my math lab, you may have that happen in some of your problems where one of the intercepts is a fraction, but my math lab will give you a grid in your coordinate plane where you can actually plot a fraction. So if that happens, you will still be able to plot it. All right, so here are all your equations of your lines. And this little chart here, this table, is in the notes that I provide for you for chapter 2. All right, section 2.4, rate of change. Before we talk about rate of change, we're going to talk about parallel and perpendicular. Lines that are parallel have the same slope. So if you're sitting in your home or you're at school, if you actually made it to school, what does parallel mean? Parallel means two lines that never touch or intersect. So if you look at the ceiling of your building and the floor of your building, they should be parallel. Now, if your house is well constructed, they should be parallel. Okay, what's perpendicular? Well, if you look at a wall and the floor, they should be perpendicular to each other. They should be at right angles. So parallel means they have the same slope. Perpendicular, we'll talk about that in just a second. So two lines that are parallel have the same slope. So then how would you find the equation of a line given a point and that it's parallel to a given line? Well, if it's parallel, then it has the same slope. Parallel lines have the same slope. So to find the equation of the line, we plug and chug. So here is point slope form. And if they ask me to put this in slope intercept form, so this is point slope. I'm going to go ahead and solve for y. Remove the parentheses by distributing the x across. Add the 5 to both sides. So that is in point slope form, an equation that has the same slope as this one, but has a different y-intercept. And that's what would make them parallel. If they have the same slope, so the constant in front of the x is identical, but the y-intercepts are different. So the first line had a y-intercept at 1, the second line has a y-intercept at 11. All right. What about perpendicular? Well, if I take a line whose slope is c over d, and I take that line and I rotate it 90 degrees, what happens? Well, this rise right here gets rotated 90 degrees and becomes a run. And not only does it become a run, it becomes negative. That arrow is pointing up, and as I rotate it 90 degrees, that arrow is now pointing to the left. My run here is d. As I rotate that 90 degrees, that run to the right becomes a rise up. So the slope of the line perpendicular to the given line, look at the difference. The slope of my line that I'm given is c over d. The slope of a line perpendicular is negative d over c. So if you took those two slopes and you multiplied them together, they're reciprocals. Number one, c over d is the reciprocal of d over c. If I multiply them together, if I multiply a number times its reciprocal, I get 1. But since I have the slope of the line perpendicular is negative, then the product of their two slopes is -1. So lines are perpendicular if the product of their slopes is -1. Okay, practically, what do you need to know? If I have a line that's given to me, a line that is perpendicular to that line will have a slope that's the negative reciprocal of the line I'm given. For example, find the slope of any line that's perpendicular to the line whose equation is x plus 3y minus 12 is equal to 0. So they gave it to me in general form. How annoying. I need to find the slope of this line. And then I'm going to take that slope, find the reciprocal, and change its sign. And that will be the slope of a line that's perpendicular to this one. Okay, so I need to find the slope. So I'm going to solve for y. I'm going to move the minus 12 over by adding it to both sides. So if it's negative on the left-hand side, it will become positive on the right. I'm going to get the x over to the right-hand side. So I'm going to subtract x from both sides. If it's positive on the left, it'll be negative on the right. And then I'm going to divide everything by 3. 3 divided by 3 is 1. Then I have negative x over 3. There's an understood 1 in front of the x. So I'm going to write that as -1/3 x. There is always an understood coefficient of 1 on any variable where you don't have a number. That 1 is understood. And then 12 divided by 3 is that 4. So what's the slope of a line perpendicular? So my slope is -1/3. So what I do to find the slope of a line perpendicular to this one, I take the reciprocal, so I flip it over, and then I change its sign. Slopes are negative reciprocals of one another. So I flip it over to find the reciprocal, and then I change its sign. So the slope of a line perpendicular to that one that's given is 3. Woo! Well, I almost got through the entire presentation without PowerPoint having a spasm. Oh, yeah. There we go. If there's a will, there's a way. Maybe not so much. There we go. All right, rate of change. Slope is defined as the ratio of the change in y to a corresponding change in x. It describes how fast y is changing with respect to x. For example, if I draw two lines, so let's draw one that looks like this, and then let's draw one in a different color. If my PowerPoint, well, it's not going to cooperate. Let's draw one that looks like this, and we'll give them the same x-intercept. Why not? This line is changing faster than that line. And the reason is because it's steeper. So a corresponding change in y over x is going to be greater for the first line I drew than the second line that I drew. Because slope does describe this change in y over the change in x. For linear functions, slope may be interpreted as the rate of change of the dependent variable, in our case, x, per unit of change in the independent variable, in this case, y. And they don't have to be x and y. They can be any two variables you want to use. Okay. There we go. All right, so let's look at this example. In 1990, 9 million adult men in the United States lived alone. In 2008, 14.7 million adult men in the United States lived alone. So it increased from 1990 to 2008. The number of adult men living alone has increased. So my slope is positive. As x gets bigger, y is also getting bigger. As the years progress, the number of adult men living alone increases. So the slope is positive. Use this information to find the slope of the linear function representing adult men living alone in the United States. And you'll notice that it's telling me that it is a linear function. It's a line. Express the slope correct to 2 decimal places and describe what it represents. All right, so I have given to me in this problem 2 points. The first point is right here, the 1999 million. So what's the dependent variable and what's the independent variable? Well, the fact of the matter is the number of adult men living alone depends on what year you're in. In 1990, it was 9 million. In the year 2008, it was 14.7. It increased to 14.7. So our x variable, our independent variable, is going to be year. And our dependent variable is going to be the number. So the 2 ordered pairs I'm given then is 1990, 9, and 2008, 14.7. So I can find the slope. So change in y over change in x. I think that's 28, 5.7 over 20, and I get 0.32. Okay, what's that mean? Well, let me write it where we can see it. The numerator of my slope, the 14.7 and the 9, are millions of men. And the denominator, the 1990 and the 2008, were the year. So what this says is the slope is 0.32 millions per year. And since it's linear, what does that mean? It means that every year, the number of adult men living alone is increased by 0.32. So if it's 9 million in 1990, in 1991, it's 9.32 million. In 1992, it would be 9.64 million, etc. So every year, the number of adult men living alone increases by 0.32 million. So that's how we interpret the slope for this particular example. And since it's linear, it's exact every year, 0.32 million every year. Oh, thank you. You know, it would be nice if I could subtract in my head, but apparently I can't. I still think it's 0.32, is it not? Is 5.7 divided by 18.32? I believe so. Thank you for correcting me. Listen, honestly, I do appreciate you correcting me. I am not kidding, because I hate to get through entire video or class and get to the end and say, oh, gee, I made a mistake there. Then I have to correct myself. Take a slurp of coffee, see if that helps. All right, so what if, PowerPoint annoys you. What if your function's not linear? I don't care. Because now I'm going to look at the average rate of change. So this graph that I have here is obviously not linear. I have the growth of a male child from birth to age 20. And as most adults, or excuse me, most human beings, growth is sporadic. It spurts. I have a 4-month-old grandson, and I didn't see him for 2 weeks, and the kid grew 2 inches. So, you can get, and I'm not kidding. So you get these spurts of growth. So what if we want to know, for example, how much he grew from age 13 to age 18? Now I could find the rate of change between each of these ages, but I just want to find on average what this kid grew from age 13 to age 18. So I can take this curve, which it is, it's not a line, and I can connect those 2 points using a line. And it's called the secant line. So when I join 2 points on a curve with a line, that's called the secant line. And I can find the slope of that. I can find the slope of a line. If given 2 points, I just plug it into the formula. Now, what I'm finding, again, is the average growth of this male human from ages 13 to 18. I'm not finding exactly how much he's growing each year, although I could do that. That's not what I'm doing here. And we notice that from age 13 to 15, he had a steeper growth period from 13 to 15 as he did from 15 to 18. He slowed down a little bit from 15 to 18. But I don't care. I'm going to find the average rate of change. So to find the average rate of change of a curve, given 2 points on that curve, I just find the slope of the line that connects them. Okay, so the 2 points are, when he's 18, he's 76 inches tall. When he's 13, he's 57 inches tall. So again, and let's talk about that. I didn't talk about that. His height depends on how old he is. So my independent variable is his age, and his height is my dependent variable. His height depends on how old he is. So we're going to find the slope, if PowerPoint will cooperate. So to find the slope, we find the change in y over the change in x. So we take the 76 minus 57, which is 19, 18 minus 13, which is 5. So we find 3 4/5. So what's this mean? It means on average, from age 13 to 18, this guy grew 3 4/5 inch per year on average. He did not exactly from age 13 to 14. Well, maybe he did, I don't know. He didn't most likely from age 13 to 14 grow 3 4/5 inches. And as a matter of fact, we do know, just looking at this, from age 17 to 18, he did not grow 3 4/5 inches exactly. But on average, in those 5 years, he grew 3 4/5 inch per year. So this is an average rate of change of this guy's height versus his age. All right, so on average, he grew 3 4/5 inches per year. And we can find the average rate of change of any function given 2 points. All right, we'll just use the mouse. All right, so the average rate of change of a function is given by this formula. Let x sub 1, f of x sub 1. So here's my first point. When x is this value x sub 1, its y value is the function value f of x sub 1. So remember, y sub 1 and f of x sub 1 are the same thing. And x sub 2, f of x sub 2. So y sub 2 is the same thing as f of x sub 2. Be distinct points on the graph of a function f. The average rate of change of my function f from x1 to x2 is f of x2 minus f of x1, the change in y of the secant line, and the secant line is that line that joins those 2 points, divided by the change in x. So that is the average rate of change of that function between those 2 points. And we do this all the time in calculus. As a matter of fact, my business calculus spent a whole section finding average rate of changes. They just did that. They just finished it. All right. I will remember to use my mouse over here. Okay, so the average rate of change is given by this formula here. F of x2 minus f of x1 divided by x sub 2 minus x sub 1. All right, so let's find then the average rate of change of the function f of x equals x to the third from x sub 1 equals -2 to x sub 2 equals 0. All right, to find the average rate of change, we need to find the change in the y over the change in x. So I need to find f of x2, and I need to find f of x1. Because they tell me x sub 2 is 0. So I need to evaluate this function at 0. It'll cooperate. So I need to evaluate this function at 0. So to evaluate that function at 0, I replace the x with 0. So f of x2 is 0. Then I'm going to evaluate f of x1. So I'm going to evaluate the function at -2. So if I cube -2 times -2 times -2 is -8. So f of x1 is -8. And then we're going to divide that by the change in y. Excuse me, x. That's x. X is in the denominator. So I get 8 over 2, which is 4. So the average rate of change of the cubic function from -2 to 0 is 4. Average rate of change is 4. So if I go and look at the graph of this thing, this is the standard cubic function. This is one of your functions that you're going to look at in section 2.5. So here we are at -2. When x is -2, oh, yikes. X is -2, y is -8. Right there. And when x is 0, y is 0. So what we did is we connected these 2 points with a line. Well, that's terrible. Let's see if I can do a little better than that. This is where you need the straight edge. And this is the secant line. And the slope of that line, the rise of the run, we're going to go up 4 and over 1. Because we go up 8 and over 2. So up 8 over 2 to get from one point to the other. So the slope is 4. Now, that is obviously not the slope of that curve, but the average rate of change is the slope of the secant line as we go from one point to the other on the curve, on the function that's a curve. All right. This is the section that I'm going to have you do on your own in the next week. It's section 2.5, and it looks daunting, but it actually is not that much, believe it or not. The first half of this section just is on the 7 common functions and their graphs, their domains, and their ranges. So these are the 7 functions you should be familiar with. You should be familiar with what the graph looks like. Now, certainly, these are all functions. You can graph all of these on your calculator. Your calculator will graph functions using the y equals button. You can certainly graph all these on your calculator to remember what they look like, but you should also know their domains and ranges. Some functions have restrictions on their domain, like this one. The standard square root function has a restriction on its domain because in real numbers, you can't take the square root of a negative. So the domain of this thing is restricted to only non-negative real numbers. Can't put a negative in there and take the square root of it in real numbers. And I think that's the only one that has a restriction. The rest of them are not. There's no restrictions on the rest of these. So just be aware that you may have a restriction on your domain, which is the case here. Now, it also restricts its range. When you take the square root, it'll always be positive. So the domain and range of that particular function is from 0 to infinity. So be aware of that. So I want you to go, and I'm going to remind you now that I have a few more on the call. Get out of here. And I'm going to go back over to Blackboard. And just as a reminder, if I go into Blackboard to course content, and then I go to the particular chapter I'm in, we're in chapter 2, and I go down to the bottom of that window, there's a folder that says Professor Castle's Lectures, and these are actually videos I have done for each section. So I do want you to watch at your convenience section 2.5 on the transformation of functions. Another reminder. Oh, see, I knew this was going to happen. I'm having issues with Blackboard. I kind of hoped that wouldn't happen in the middle of a Zoom call, but it did. If I go back to course content in Blackboard, and I go to your particular chapter, functions and graphs, and go to a particular section, there are videos that are available from Pearson also. So there are, gosh, 7 videos just on this section alone. And there are little short clips of videos, little short videos. Are there any questions? All right, well, I'm going to stop the recording.